Hi guys, I'd like to welcome all of us to my channel of Honesty Sciences and Mathematics TV channel. I'd like to request our members to kindly go to YouTube and search Honesty Sciences and Mathematics TV channel. Subscribe and engage us in the comment section so that we can be having a series of discussions on various topics in mathematics, chemistry, physics, and biology, and other related topics. So today we're going to look at an aspect of our work which is going to be done in isothermal expansion of a gas. Now, this specific term that I've used in this particular case refers to the concept of a constant temperature, and therefore we are going to employ that one in trying to describe the concept of a work insofar as expansion of a gas is concerned. Now, on my left side of the board, I've given an illustration, which is of course going to be a chamber that is consisting of a gas that is undergoing this isothermal expansion. So I'm going to have this temperature, which is going to be constant, of course, being applied in this specific system. And as the gas expands, we're going to see that I can be able to describe the initial volume of a gas, V1 given as such. And then we are going to have the second aspect, which is going to describe the final volume of a gas, which is going to be given as V2. So therefore, we can be able to describe this specific aspect whereby the gas is going to be expanding at a constant temperature. Now, of course, in this particular state, we're going to see that for this gas to expand under constant temperature, we're going to see that there's going to be involvement of an aspect of the external pressure, and of course we can be able to describe the aspect of internal pressure in this particular case. If we try to look at this, of course, for it to expand under constant temperature, the external pressure is going to be decreasing at a particular rate, whereby the internal pressure, of course, is going to be increasing in this specific case. Of course, in actual sense, we can be able to describe this particular aspect of the internal pressure as undergoing some specific adjustment in order to cater for this specific expansion of this particular gas. So we're going to look at it in terms of an adjustment contrary to the expansion that I've mentioned, and of course we're going to elaborate deeply on that specific aspect, especially when we're going to go further in this specific discussion. So therefore, we can be able to describe this particular aspect of external pressure, the relationship between external pressure and internal pressure, whereby we're going to see that we can be able to describe this aspect of internal pressure and at any given point during this process of expansion by giving it as, of course, the pressure minus the change in that small pressure, which is going to be, of course, accompanying that adjustment given as dP, where dP, as I've said, is going to be the infinitesimal change in the pressure which is going to be, of course, experienced. So my P is going to represent what we refer to as the internal pressure, and therefore from this particular aspect we can be able to describe the work that is going to be done when the gas is going to change this particular volume by delta, or just dV, from this aspect of work that I mentioned earlier. So therefore the small change or an element of work that is going to be experienced from this can be given as sigma W, which is going to be work, of course, which can be described as the small change in pressure, which is external, of course, internal pressure minus this small adjustment in pressure given as dP, and therefore that is going to be given as a change in pressure times the change in volume, which I've given as such. So this is going to be the change in small change in volume, and this is going to be the change in pressure. So we can be able to give this element of work as the change in pressure, which is internal pressure minus the adjustment in pressure, of course, minus, times the change in volume given as such. So this is going to give us an element of work, and the summation of these small elements of work is going to give us the overall work which is going to be done given as the pressure, and then change in volume given as dV. So this, of course, is from the first aspect that we are seeing using the concept of describing the aspect of work. Therefore, we can be able to give the whole aspect of work of change in volume from between V2 and V1, of course, which is going to encompass this upper parts. And therefore, in terms of an equation, we can be able to describe this element of work in terms of initial and final volume using this specific integral equation, whereby we're going to have work being given as the integral between the final and the initial volume, of course, which is going to be given us pressure and change in volume given us that, whereby we have said that V is going to be the initial volume and W is of course going to be work, and P is going to be describing what we refer to as the pressure. Now from the ideal gas equation, we can be able to quantify this specific change or rather specific element of work by using this equation of PV is equivalent to nRT. Of course, I presume that we are going to comprehend on this from the ideal gas equation. This pressure times volume is equivalent to N, where N is the number of moles of a gas, and this is of course going to be a constant, and this is going to be absolute temperature given in terms of a T. So we can be able to describe pressure from this specific equation by giving it in terms of nRT over V given as such. And of course, from this particular case, we can be able to represent pressure in terms of this specific element constituting the number of moles from a specific equation of the ideal gas equation, of course, and substitute it in this particular case. If we are trying to describe work for any number of moles, whereby we have said that N is going to constitute the number of moles of this specific gas, and that is going to assist us, calculate that aspect of work. So therefore, we can be able to give work in terms of the N number of moles, the change in volume between V2 and V1, whereby we're going to have pressure represented as nRT over V, and then we're going to have dV given as such. So if you try to look at that specific work in terms of a number of moles, we can be able to do an evaluation of this for V2 and V1, and therefore we're going to have work represented as we said, the number of moles are going to be constant, nRT, so therefore we're going to take them outside the integral sign, and that is going to be between V2 and V1, and therefore we're going to find dV over V given as such. So this basically is going to reduce into a form which is going to first. Now from our integral calculus, we're going to have that one reduced into a form of an nRT, and then we're going to have the natural log of a V, which is a V2 over V1 given as such. So this is going to constitute the work that is going to be done, of course, due to change in that specific volume. And of course, I've mentioned the concept of adjustment in pressure, which I've given us, of course, P, which is external pressure, minus dP. And of course, we can be able to give that one, of course, in terms of pressure whenever the temperature is going to be constant. And therefore, from a combined gas equation, we can be able to give a description of pressure and volumes under constant temperature using P1 V1 is equivalent to P2 V2 given as such. So for us to describe the relationship that is going to be given in terms of pressure and volume, we're going to see that this P1 over, or rather this aspect of V2 over V1, in this particular case, this division, if you try to, okay, let me do this. If you try to do a division over V1, we're going to have this one cancel, and therefore we're going to have P1 over P2 is equivalent to V2 over V1, and this is going to depict an inverse proportionality between these two aspects of pressure and volume. So therefore, we can be able to describe this aspect of work alternatively using the concept of pressure at constant temperature by giving it as W is equivalent to nRT, of course, the natural log of pressure 1 over pressure 2 given as such, which is going to give the relationship between this one at constant temperature given as such. So the aspect of constant temperature that I've mentioned, of course, is the one that I've referred from our first description of the concept of isothermal. Therefore, we can be able to give maximum work done in isothermal expansion of a gas using this two specific reference for volume and pressure given as such from the ideal gas equation and the combined gas law, of course, using those two specific aspects. So I hope that we have understood how we can be able to describe works in terms of those two specific equations, the isothermal expansion of a gas. So catch us in our next video where we're going to look at different aspects of this particular aspect of our work, especially if we are going to consider the aspect of pressure, volume, and temperature, and other circumstances which I'm going to mention in those specific discussions. So that is it for now, guys. Kindly subscribe to our channel and check in our description boxes for various links of other related videos and content. So that is it for now, guys. Bye, God bless.